So the section 6.4 was about volume. Very quick reminder, what we did was, let's say that we have two functions. Maybe one is a function f. Let's say this is my coordinate system. This is the x-axis. This is the y-axis. Let's say we have two functions. Maybe one is function f. So this is my function f. Let me admit this person. Okay. Sorry, so the function f is given. Let's take another function, maybe function g, something like that. I have two functions, f of x and g of x. And I'll be assuming that the function f is less than the function g. So we have this situation. Let's say the functions are defined from some point A, maybe from some point A, all the way up to some number b, two functions. And now what I want to do is I want to look at the region enclosed by those two functions. So I'm looking at the region enclosed by those two functions, and also this straight line and this straight line. And what I want to do is I want to do the revolution about the x-axis or about the y-axis or any other line. For example, I'll do the revolution about the x-axis, but so something like this. So what I have here, I have this region enclosed by those two functions, and I'm doing the revolution about the x-axis. So what I get is I will get a three-dimensional solid. So let me try to sketch the, not sure if I know how to do this, but when I do the revolution about the x-axis, this is supposed to be something symmetric. So something like this, and this is the other function. Okay, so that will give me something like this, and then something like this, and then something like this, and then something like that. Okay, so that's a three-dimensional solid that we obtained by doing the revolution of the region about the x-axis. Okay, so here are those two functions. This is a function f, and this is a function g. And let's say
two functions on symmetrical AB as shown in this picture. Consider the shaded region enclosed by the functions and by the two vertical lines x equals a and x equals b.
This is the region that will be.
Let's rotate this region about the x-axis to get the solid of revolution. This is the three-dimensional solid of revolution that is unfolding in this picture. Let's call this solid S.
Oh, okay, so the two functions were given. We had this region enclosed by those two functions, and then we do the revolution about the x-axis, and we get the three-dimensional solid S. Let's call this solid S, for example. Then the question is how to compute the volume of this solid. So we'll be doing. So I'll draw this again very quickly. This is the y-axis. This is the x-axis, and I have one function like this, and maybe another function like that. And then the functions are defined from some point A up to some point B. And then when I do the revolution about the x-axis, I get a three-dimensional solid, the volume of which I want to compute now. So maybe I don't want to draw this solid. I don't really know how to do this, but the solid is the one that we just saw in this little video. And so very quickly, like this is symmetric, so something like this, and then something like that. Okay, so we have this solid S. And the question is how to compute the volume of the solid. So key idea is the one that we always do, and we'll look at the cross sections. So I'm going to take any point X in between A and B. So I'm going to take any point X in between A and B, and I'm going to look at the corresponding cross section. So maybe this is my point X, and then I'm going to take a piece of paper and I'm going to cut the solid through in this way. So when I do so, I'll get a cross section, and my cross section will look like this, something like this, and then something like this. And that's the solid I want to compute the volume of. So see, here's how we'll be computing the volume of this. So first of all, take any point x in between A and B. Take any point x in between A and B. So here's my point x, anything between A and B. And then we'll be looking at the cross section that corresponds to this given point x. And the cross section is simply the intersection of this three-dimensional solid with a plane. So I'll take a piece of paper and I'll cut this solid through orthogonal to the x-axis. So this piece of paper will be something like this, something like this, something like this. Okay, so this is the cross section, and I want to compute the area of the corresponding cross section. That's a cross section that corresponds to this given point x. So the area of this cross section that is given by this point x is going to be equal, let's see, the area of this big circle, the area of this big circle is going to be pi times the radius of this circle, but this is exactly f. So the function was f. So this is exactly f of x. And then what I want to do is I want to square this. That will give me the area of this whole circle, but I have to remove from that the middle small circle. So I have to say minus, and then the area of the small circle. So this is pi times the radius of the small circle is this one, which is, if this function is called g, then this will be g of x. G of x. And then I have to square it. And this is exactly the area of this cross section that corresponds to this given point x. Okay, and last thing to do to compute the volume of this solid S, what we do, simply we integrate from A up to B of those cross sections A of x dx. A of x dx. And this is excuse me, this is exactly the volume of this three-dimensional solid. So let me give you a specific example. Okay, so in this example, I want to find the volume of the solid that is obtained in the following way. So first of all, I'll take this function y equals square root of x. Okay, so let me sketch the graph of this function for you. So here's the y-axis. Okay, and then here's the x-axis. Okay, how does the function square root of x looks like? Very simple. It's like at 0 is equal to 0, and then something like this. So that's the function y equals square root of x. And it says consider this function not for all values of x, but only for x's between 0 and 1. So here's 0, and then here's 1. Okay, so now let's look at this region underneath the function square root of x. Let's look at this region underneath the function square root of x. And now let's do the revolution of this region about the x-axis. For example, so this is the region we're looking at now. And when I do the revolution about the x-axis, that will give me a three-dimensional solid, the volume of which I want to compute. So this is supposed to be symmetric, so something like this. And then we get a three-dimensional solid that looks like this, something like that. Don't know if I know how to draw this, but okay, so this is the three-dimensional solid S. This is the three-dimensional solid S, the volume of which we want to compute. So very simple, because first of all, cross-section. So for any point x, in between 0 and 1, for any point x in between 0 and 1, I will be looking at the corresponding cross-section. So the cross-section is, we take a piece of paper and then we cut the solid through that way. And this piece of paper will go through this given point x. So let's say this is my point x. Maybe it's here. Maybe it's here. And then I'll take a piece of paper, I cut the solid through orthogonal to the x-axis, and then what we get is we get a cross-section that corresponds to this given point x, and the cross-section will look like this. So I'm not sure I know how to draw this, but okay, so that would be the cross-section that corresponds to this given point x. Okay, question for you, what is the shape of this cross-section?
Circle.
Perfect. This is exactly right. This is circle. So something very simple because we know how to compute the area of circle. So now I want to compute the area, not the volume, but the area of this cross-section that corresponds to this given point x. So the area of the circle is very simple because this is pi times, and then I have to take the radius of the circle, and I have to square it. Okay, another question for you. This is my cross-section that corresponds to this given point x. We know that the shape of this cross-section is a circle. Of what radius? What is the radius from here to here? What is the radius of this cross-section, the radius of the circle?
The square root of x.
Perfect. This is exactly right because see, this is the function square root of x, and at this point, this is exactly the square root of x. So the radius is square root of x. Okay, and the reason I want to square it because if I have any circle, and if this is the radius, then the area of the circle is pi times the radius and square it. Okay, so we know that. So let's simplify this formula for a of x. This is simply pi times x. Okay, and last thing to do to compute now the volume, of the solid S, this is going to be indefinite integral from 0 to 1, of this function a of x dx, which in this specific example is this function pi times x, dx. Okay, integration is a homogeneous operation, meaning that if I have constant times a function, I can pull out this constant outside of the integration symbol. So let me admit this one person. Okay, integration is a homogeneous operation, meaning constant times the function. I can pull this constant outside, and then this is integral from 0 to 1 of this function x dx. And now, question for you, very, very simple. What is this definite integral equal to?
Pi over 2.
Perfect. This is exactly right. This integral itself is 1/2, but you have already multiplied this by pi, which is pi over 2, which is perfect. This is exactly pi over 2, and this is the volume, and that's it. Well, of course, we can use either to compute this integral itself, either you can use the fundamental theorem of calculus, or look, what we have is very simple. We have this function y equals x, and you want to know what this definite integral is from 0 to 1. But this is simply the area of this triangle, which is 1/2. And then you multiply this by pi, and you have pi over 2. And that's the volume of this three-dimensional solid S. So let me give you just one more example, and then we'll be doing new section. But Okay, so we just did this example, but let me say just very quickly. The function was y equals square root of x. That was the function. That was the function. Let me admit this one person. Exactly. Antiderivative of x is x squared by 2. You're exactly right. You can also compute this definite integral using fundamental. Absolutely, yes. So let me just say very quickly what we did was the function was y equals square root of x. And I took this function, and then let's say I consider this function for x's between 0 and 1. For example, I can do from 0 to 7 and so on and so forth. Just for example, consider this function for x's between 0 and 1. And when you do the revolution of this function about the x-axis, then you get a three-dimensional solid, which looks like something like this. Okay, and then, okay, so you take any point x in between 0 and 1. So for example, maybe this is my point x. And then you cut this solid through orthogonal to the x-axis by a piece of paper. So when you do so, you get a cross-section that corresponds to this given point x. And the cross-section is simply a circle. So here's the cross-section that corresponds to this given point x. And notice one thing, when you will be changing this point x in between 0 and 1, then this cross-section will be changing, and so will be its area. So the area of this cross-section that corresponds to this given point x is a function of x. So a is a function of x, and the area is very simple because it's pi times the radius squared. But the radius is square root of x. And when you square it, that will give you just x. And to compute the volume of this three-dimensional solid, volume is not the same as the area, you know. We'll be computing the volume of this, then the volume will be simply integral from 0 up to 1, 0 up to 1 of this function pi times x dx. So integration is a homogeneous operation. This is pi times integral from 0 to 1 x dx. Use fundamental, for example, so this is pi x squared divided by 2. This is antiderivative of this function. Indicate that you want to know what this function is equal to at 0 and what this function is equal to at 1. At 1, this function is equal to 1/2. When you multiply this by pi, that will give you pi by 2 of some units cubed. Okay, so this is exactly the volume of this solid, which is obtained by rotation of this region. So see, initially what we have was this function y equals square root of x, and then we consider this region. And then, well, we know how to compute the area of this region, but that's a different question. What we wanted to do, we just took this region and we did this rotation about the x-axis. And then we have obtained a three-dimensional solid. The volume of this solid obtained in such a way is pi over 2 some units cubed. Also, as a practice problem, I would like to ask you, it's not a homework, but if you like to ask you, you can do, so the same function, excuse me, the same function is square root of x. But now, let's do this revolution about the y-axis. Exactly the same idea. So you get a three-dimensional solid that looks like something like this. It's kind of like a cone, but so you get a three-dimensional solid S, and you can compute the volume of this one. So exactly, for example, units cubed. So for example, if on this axis I'm using centimeters, so from here to here is in 1 cm, then this would be pi over 2 cm cubed. And if on this axis I'm using different units, maybe u, then that would be u cubed. Okay, another example, but idea exactly the same. So very quickly, very quickly. So we have two functions. One is the function y equals x. So here is the function y equals x. So the function is like this. Y equals x. And here's another function y equals x squared. So the function y equals x squared looks like this. So that's the function y equals x squared. Okay, and those two functions enclose a region. Well, that's this region. I don't want to shade it, but that's the region enclosed between those two functions, so to say. So I want to do the revolution about the x-axis of this region, and then I'll obtain a three-dimensional solid. I want to compute the volume of this solid obtained in such a way. So first of all, we need to find this intersection point, which is obvious, which is very simple because one function was x and the other function was x squared. And we want to know for what value those two functions are exactly the same. But what is the solution of this equation? X equals which point?
1.
Perfect. This is exactly right. So x equals 1 is solution. And see, at 1, those two functions are equal. So now let's do the revolution of this region about the x-axis. Then we'll get a three-dimensional solid that looks like this. So something like this. Okay, and let's compute the volume of this solid. So first of all, take any point x in between 0 and 1. So here's my point x, for example, and let's do cross-section orthogonal to the x-axis. And then when we do so, the cross-section will look like, that'll be something like this. But then there'll be another circle inside. So this is how this cross-section will look like. So this cross-section will look like a circle with a circle removed inside, like a washer, something like this. And then let's compute the area of this cross-section that corresponds to this given point x. But notice one thing again. When you will be moving this point x to the left to the right, the cross-section will be changing, and so will be its area. So the area A of this cross-section is a function of x. Okay, so let's compute the, okay, what is the shape of this cross-section? What would be the shape of this cross-section?
Circle.
Perfect. So the shape of this cross-section would be one circle, and then there's another one, the small one, and the shape of this cross-section will look like this. So it's like a circle with a small circle removed from inside, like a washer. So now what we have to do is we have to compute the area. So it's very simple because what we do is we take the area of the big circle minus the area of this small circle. So let's do first one, the big circle. So this is pi times the radius. Okay, what is the big radius from here to here?
X pi x squared.
Perfect. So the radius itself is x, and the whole thing will be pi x squared. So this is perfect. That's exactly what you are saying. And then what we have to do is we have to say minus, and then we have to remove the small tiny circle inside. So pi times what is now this small radius?
X squared.
Perfect. The small radius is x squared, and I have to square it because I want to take the area of the circle. So let's simplify this function a of x. A of x is simply going to be equal pi times x squared minus pi times x to the fourth. So this is exactly the function a of x. This is the area of the cross section, but notice one thing, the area A depends on the position of this point X. For example, when you go all the way up to 0, then this is 0. Okay, so now to compute the volume of this three-dimensional solid, very simple, it's integral from 0 to 1, from 0 to 1 of this function a of x. So it's pi x squared minus pi x to the fourth dx. Okay, so for that, I have to use fundamental. Okay, so this is going to be pi times, okay, antiderivative of this function x squared is x cubed by 3 minus antiderivative of x to the fourth is what function?
X to the fifth.
Perfect. X to the fifth divided by 5. Okay, and then I have to just indicate what this function is equal to at 0, and then what this function is equal to at 1. So at 1, this is simply going to be equal pi times, this is 1/3 minus 1/5. But then at 0, the function is 0. So this is the answer. So the common denominator will be 15, and then we'll have 5, so it's like 2 pi over 15. Okay, this is the volume. 7.1 section is essentially about differential equations, some modeling with differential equations as well. So first thing I want to do is I would like to tell you what is a differential equation at first place, because we'll be using it. So the first question will be, what is a differential equation? You know, that's a simplification in many ways, but essentially, it's a simplification in many ways, but essentially you can divide the category of all equations into two. One, you might have algebraic equations, something that we study in school, in elementary school, and then on the other hand, we have differential equations, ODEs sometimes, differential equations. So for example, an example of an algebraic equation could be find all numbers x such that, I don't know, 2x equals 1. This is an example of an algebraic equation. Okay, so what is the unique solution of this algebraic equation? X is equal to what point? Well, okay, something very simple. But now I want to look at a little bit different. This is going to be also an equation, and the equation says this: find all functions See, here's the fundamental difference. Here, I am looking for numbers like 1, 2, 3, 4. I'm looking for numbers x that satisfy some condition or some equation. Here, I will be looking for functions that satisfy some condition or some equation. So let me do a simple example. The equation will be find all functions y such that and here that was the algebraic equation, and here I'm going to have an analog of my equation, and the equation is, so find all functions y such that y prime, so derivative, equals y. See, this is the difference. On one hand side, you might have algebraic equation, for example, 2x equals 1. I'll give you another example. Maybe find all numbers x such that, I don't know, x squared is equal to maybe x another equation, and so on and so forth. This would be an algebraic equation. On the other hand, the beginning is almost the same. It says find all functions, but here's the difference. We'll be looking for functions as opposed to numbers. Perfect. Someone gave me exactly the very good solution, one solution of this differential equation. See, what is a differential equation? Differential equation at first place is an equation. What kind of an equation? Equation is a functional equation because functions are involved in this equation, but not only function, also derivative. So it's differential equation. And that's all this section is about. Differential equation we'll be solving. And here's a simple example of a differential equation. So what this differential equation says is essentially it says the following: find all functions, differentiable obviously, but find all functions y with the property that the function and its derivative are exactly the same. So question for you: could you give me an example of a function that satisfies this differential equation? In other words, could you give me an example of a function derivative of which is exactly the same as the function itself?
e to the x.
Perfect. This is exactly right. One solution is the function e to the x. One solution is the function e to the x, because the derivative of e to the x is the same function. But could you give me also another solution? Could you give me another solution, different function that also satisfies this differential equation? Okay, so let's see. Take this function y equals 2 times e to the x. Take this function 2 times e to the x. And let's see if this function satisfies this differential equation. Well, I'll have to compute derivative of this function. Then derivative of this function, taking derivative as well as taking antiderivative, is a homogeneous operation, meaning constant times a function will be the same as constant times derivative of this function e to the x, but derivative of e to the x is the same function. So notice one thing: the function and its derivative are exactly the same, meaning that this function y equals 2x is also a solution of this differential equation. Could you give me another example of a function that is a solution of this differential equation? One function was e to the x, and then we check that also y equals 2 times e to the x is also a solution to this differential equation. Could you give me one more example of something that is a solution of this? See, so if you consider this function y equals take any constant c. C could be any number, for example, 1 or 2 or 7 or anything, and then c times e to the x. Well, let's compute the derivative of this function y prime. So taking derivative is a homogeneous operation, so this is going to be c times derivative of the exponential function, which is the exponential function as well. And again, c times exponential equals c times exponential, so y equals y prime. So in other words, this function is a solution of my differential equation. So, okay, so example of a differential equation is this one: differential equation. Example, y prime equals y. And what this differential equation says, that it says that I want to find all functions with the property that the function and its derivative are exactly the same thing. And the general solution of this differential equation would be if you take any constant c and consider this function c times the exponential function times e to the x. So this is the general solution of this differential equation. general solution of this differential equation. So let me show you. So c times the exponential function. Let me show you a few solutions of this differential equation. So this is one solution of this differential equation, y equals y prime. Another solution of this function is if you take 2 times e to the x. This is another solution of this differential equation. Take 3 times e to the x, another solution. Or take maybe 1/2 or 1/5 e to the x. And take maybe 1/100 times e to the x. This is another solution of this differential equation, and all those functions with negative. So I'll take -1 divided by 100 e to the x. This is another solution of this differential equation. Let's say maybe -2 e to the x. This is another. So this is the family of solutions of this differential equation, y equals y prime. This is exactly the solution set. The set of all solutions to this differential equation looks like this. This is a collection of exponential functions c times e to the x, where c is any constant. Okay, so I just show you a couple of solutions to this so the differential equation was y equals y prime. The general solution are functions of this form c times the exponential function. This is the set of all solutions of this differential equation. And we just saw a few of them. When you take the constant c 1/100, you get this solution. If you take -7, you get this solution, and so on and so forth. So one thing that's important, that is useful when we study differential equation, is something that's called the slope field or directional field, sometimes it's called. And this is basically the collection of tangent lines to all those functions e to the x. For example, you can just see that one solution will be the function 0. The function y equals 0 is one solution of this differential equation, y equals. If you take c equals 1, this is probably the exponential function somewhere here. And here's another solution of this differential equation, and here's another solution, and so on and so forth. And those arrows basically will guide you how to draw a few solutions to this differential equation, y prime equals y. Okay, so let me give you another example of the differential equation, a simple one. So y prime equals 0. This is a differential equation, and this differential equation says find all functions y with the property that the derivative of those functions are 0. Could you give me an example of a function derivative of which is 0?
Y equals 5.
Y equals 5, perfect. One example. So here's the function y equals 5. 1, 2, 3, 4, 5. And it's a constant function. Y equals 5 is one solution. Could you give me another solution of this differential equation?
Y equals 10.
Y equals 10, perfect. Another constant function. And in fact, if you take any constant c, any number, then the function y equals c is a solution of this differential equation. So all the constant functions are solutions of this differential equation, and the direction field will look like this. Just not really interesting, but constant functions are solutions of this differential equation. Take simple differential equation y equals 2. Could you give me one function that is a solution of this differential equation? In other words, derivative of your function has to be equal to. Could you give me one?
Y equals 2x plus 5.
Perfect. Excellent. So this is y-axis, and you just took this function y equals 2x plus 5. So 2x will look like this, and then plus 5. So this is 5. Then your solution looks like this, 2x plus 5. Another example, okay, very quickly, one more example of a solution of this differential equation. So you can take 2x. See, you have to take 2x because the derivative of the this would be 2. And then you take any constant c, and this is the general solution of this differential equation. Because see, if you compute derivative of this, derivative of 2x is 2. And the derivative of a constant function is 0. So y prime indeed is equal to 2. So that's a solution of this differential equation. So this is the direction field, basically all those functions 2x plus c, all those functions 2x plus c. Here is another differential equation, but we have no time today. We'll do this one on the Friday.